Hello, students. This is Mr. Allen. Today we're going to look at section 2.1, chapter 2, patterns in inductive reasoning. So begin our chapter on proof. So the objective today is to use something called inductive reasoning to make conjectures. So I think like to start this lesson with an example. So let's say we have a student, we'll call him Billy. And Billy, and let's pretend this is like a normal school year where students meet every day. And let's say on Monday, Billy comes to math class and he's tardy. And then on Tuesday, Billy comes to math class and he's tardy again. Wednesday, Billy comes to math class and he's tardy. Thursday, Billy comes to math class again, he is tardy. So he's been tardy Monday, Tuesday, Wednesday, and Thursday. What do you think that Billy's teacher might conclude about Billy being at class on time on Friday? So it's probably not hard to believe or to argue that the teacher might think that Billy's going to be tardy again on Friday. This is an example of inductive reasoning. Based on previous experience or based on a pattern, we make a conclusion. And that conclusion is called a conjecture. So inductive reasoning is a process of using a pattern or a repeated behavior to make a conjecture. And a conjecture is just an educated guess or a conclusion. So in the example of Billy being tardy to class, the conjecture the teacher may make is that Billy is going to be tardy on Friday. So let's look at some examples. Let's make a conjecture about the next term in this sequence. So I've got some numbers here, 20, 16, 11, 5, -2, and -10. And I'm trying to guess what I think the next number is, but I want to make a conjecture. I want it to be an educated guess. I'm going to try to use some inductive reasoning. So I'm going to look at these numbers, and I'm going to try to figure out if there's anything that I can conclude about them. Okay, I think I see it. They're decreasing as I go along, right? They keep going down. Now this one here went down by 4 because 20 minus 16 is 4. 16 to 11, that's not going down. Oh, that went down a little bit more. That one went down by 5. And then 11 going to 5, that'd be going down 6. And then 5 to -2, that's down 7. And then down 8. So I would conjecture that the next time to get to the next one, I'm going to have to go down 9. So my educated guess is the answer is -19 based on the pattern. Use inductive reasoning to make a conjecture about the rule for finding the next figure in the series. So now I'm not asked to find what the figure is, but what's the rule. So it looks like my first figure has some characteristics, my second figure has some characteristics, and my third figure has some characteristics. And it looks like this first figure has 3 sides, the second figure has 4 sides, and this next figure has 1, 2, it looks like 5 sides. So if I had to guess the next figure, I'm guessing the next one's going to have 6 sides. So that'd be the next one. So that'd be a 6-sided figure like this. So this would be the fourth one. And I noticed that the first one had 3, the second one had 4, the third one had 5, the next one has. So you might argue that the nth, this is kind of a harder question, but what would be the number of sides of the nth polynomial? Can you see the connection between the numbers along the bottom and the numbers on the top? I'm hoping that you'd guess that the nth one will have n plus, not minus, 4 plus 2 is 6, so n plus 2 sides. So this might be the rule, this might be the rule for that particular pattern. What conjecture can you make about the 21st term in the sequence? Wow. So they've given us 6 terms, and we're trying to figure out what the the 21st term is. So the first term is red. The second term is R. I just kind of gave that one away. This is red, white, blue. So it's red, white, and blue, and it's red, white, and blue. So the third term is blue. Then the next term is, well, it's repeating this pattern, if you will, right? So it looks like the first one is red, the second one is blue, and then or white, and the third one is blue. So, and then this is repeating. There's 3 of these here. There's 3 of these here. So here's my question. If this is the first, second, third, this would be the fourth one, right? Fifth, sixth. What do you think the 21st term would be? Would it be R, W, or B? And I'm going to leave that one for you to decide. You could just list them all out to find out if you really want to know if you're right. Okay, example 4. What conjecture can we make about the sum of the first 30 odd numbers? Now, this is why I want to show you the power of inductive reasoning. So the first, let's list the odd numbers, right? So 1, 3, 5, 7. Oops, I said 7 and I wrote 6. 9, 11, 13, etc. So those are the odd numbers. Now, I've only listed out 1, 2, 3, 4, 5, 6, 7 of them. So here's the first 7. My question is, what is the sum of the first 30 odd numbers? Now, if we wanted to, we could list out all 30 of them and add them up. But I'm going to try to use a conjecture to figure out a quicker way to do that. Well, the first sum, well, the first one is just 1, and 1 plus nothing is 1. What if I added the first 2? Well, if I add the first 2, that's this one and this one. 1 plus 3, that's 4. Okay, interesting. What about if I added the first 3? Let's see here. So that'd be these 3 here. So that's the last one, which is 4 plus 5 more. That's 9. Let's do one more here. Let's see if we can see a pattern here. So if I add the first 4, that's these guys here. That'd be 7 plus, that's 16. Interesting. So I'd like to note that 16 is the same thing as 4 squared. 9 is the same thing as 3 squared. 4 is the same thing as 2 squared. And 1 is the same thing as 1 squared. So what do we think the sum of the first 30 numbers are? Well, it's going to be, I conjecture, it's going to be 30 squared, because this was the pattern, right? The first 4 would be 4 squared, which was 16. So that's going to be 900. Now notice I didn't go through and list all 30 odd numbers and then add them up. I used a conjecture in inductive reasoning to get me to my result. Now let's talk about our final term here, which is something called a counterexample. And a counterexample is an example that shows a conjecture is incorrect. Now, I'm not going to go all the way back to my first slide, but my first slide I talked about a young man that was tardy to class every day. One of the problems with inductive reasoning is sometimes you could be wrong. So my question originally was, will Billy be tardy that 4th day? Well, he might be tardy and the teacher may be right, but the teacher could be wrong and maybe Billy is on time on Friday. So here's an example of a counterexample. Hopefully you guys are familiar with the gentleman in this picture. This is a picture of a guy by the name of Peyton Manning, and he used to be the quarterback for the Indianapolis Colts. And let's say a common stereotype that people might use, particularly if they're not fans of football, is they might say something. This is a stereotype, a generalization. But all football players are not smart. Okay, not smart, which we know that's not true, but let's just pretend that someone makes that statement. So let's talk about Billy again. I'll use Billy. So Billy says, you know what, all football players, they're not smart. So a counterexample is something that you can provide to show that a statement is incorrect. So when I say that all football players are not smart, the counterexample I might use is Peyton Manning. I may say, you know what, I don't think that that's a true statement. I think that there's this football player, Peyton Manning, and I think that he is very smart. He has a degree from the University of Tennessee, and whatever other information I want to provide. And I think most people that know who Peyton Manning is would probably argue that he's a pretty intelligent guy. And providing that one counterexample is all that I need to do to basically prove that the statement, that generalization, is incorrect. So let's see if we can see some examples of using a counterexample for a conjecture. So here's my conjecture. If the name of a month starts with the letter J, then it's a summer month. So I'm basically saying in this statement, if you give me a month, if you give me a month that starts with the letter J, then it has to be a summer month. So how would I come up with a conjecture, or I'm sorry, a counterexample for that conjecture? Well, I need to just come up with a month that starts with the letter J that is not a summer month. Can you think of any months that start with the letter J that are not summer months? Well, I would argue that January is a month that starts with the letter J that is not a summer month. That would be what we would call a counterexample. Therefore, this statement I just made is false. Let's try another one. You can connect any 3 points to form a triangle. At first, that may seem kind of reasonable. A triangle has 3 vertices, it has 3 sides, yeah. Well, the counterexample is, or could be, what if all 3 points are on a line? So let's say I got point here, and then a point there. So there's point A, there's point B, and there's point C. And let's say they are all on this line. We'll call it line L, Ritchie. So can I make a triangle out of those 3 points, A, B, C? You cannot. If you were to connect these 3 points with line segments, you would get a line segment, not a triangle. So these 3 points do not form a triangle. So this picture diagram is my counterexample. Okay, let's do another one of these, one more. When you multiply a number by 2, the product is always greater than the original number. Now that might seem true, right? So like if I pick the number 3 and I multiply it by 2, that gives me 6. Or if I pick the number 5 and I multiply that by 2, it gives me 10, so it's greater. What about other numbers though? Well, that may not be true. Ooh, what about a fraction? Like what if I used 1/2? What's 1/2 times 2? Well, 1/2 times 2 is 1 and 1. Okay, so that doesn't work. Can you think of any numbers where that's not true? Well, an easy counterexample is 0. If you take 0 and then you multiply that by 2, you get 0. Is 0 greater than the original number? Nope. So 0 is a decent counterexample to this problem. And there are others. Can you think of any other numbers that would produce a counterexample? That's all we got for today, section 2.1, inductive reasoning. Have a good day.